A storm born on the sun reach Earth days later and push invisible currents through technology we depend on.
Nothing has to strike the ground. The danger begins when charged particles and magnetic fields disturb Earth's protective environment.
The frightening question is not whether auroras appear, but whether electrical networks, satellites, navigation, and radio remain stable. Our civilization uses long conductors, synchronized clocks, orbital infrastructure, and precise signals that earlier societies never needed. In May 2024, Earth experienced its first G5 geomagnetic storm in more than 2 decades, creating auroras far beyond normal latitudes. That event caused no global catastrophe, yet it became an unusually well-documented test of how modern systems react under severe space weather.
Several coronal mass ejections left the sun in rapid succession, then compressed together before reaching our planet.
Some solar material traveled at roughly 3 million miles per hour, turning a distant eruption into a near-term forecasting problem. The same process that paints auroras across the sky can also drive currents through transformers, pipelines, and other long conductors. A severe storm does not behave like a single blast. It stresses different technologies through several linked physical mechanisms.
To understand the risk, we must follow one eruption from the solar surface, across space, into Earth's atmosphere and infrastructure.
The story begins 93 million miles away, where magnetic energy can suddenly reorganize and release an enormous burst. The sun's surface is threaded by magnetic fields that twist, stretch, and store energy as hot plasma moves beneath them. Sunspots appear darker because they are cooler than surrounding regions, but their magnetic complexity can signal intense activity. A solar flare is a sudden release of electromagnetic radiation, reaching Earth at light speed in about 8 minutes. A coronal mass ejection is different. It launches a vast cloud of magnetized plasma that can take hours or days to arrive. Flares and mass ejections often occur together, yet one is radiation, while the other carries matter and magnetic structure. Inside a CME, magnetic field lines can form a rotating structure whose orientation strongly affects what happens at Earth. When the incoming field points southward, it can connect efficiently with Earth's northward field and transfer far more energy.
That reconnection acts like opening a gate, allowing solar energy and particles to enter the magnetosphere more effectively.
Even without eruptions, Earth sits inside a continuous solar wind flowing outward from the sun in every direction. The solar wind first meets a bow shock, where charged particles slow, heat, and divert around our magnetic obstacle. Earth's magnetic field creates a vast asymmetric cavity, compressed on the day side and stretched far behind the planet. During a storm, the magnetotail can store energy before releasing it toward Earth in bursts called substorms.
Charged particles collide with oxygen and nitrogen high above Earth, producing curtains of green, red, purple, and blue light.
Stronger storms expand the auroral oval, allowing displays to appear much farther from the poles than people expect. Auroras are not the damaging part, but their unusual reach reveals that Earth's magnetic environment is being strongly disturbed. NOAA ranks geomagnetic storms from G1 to G5, describing increasingly serious effects on power, satellites, navigation, and radio. Scientists can see an eruption leave the sun, but predicting its exact arrival and magnetic orientation remains difficult. A CME can accelerate, slow down, interact with earlier eruptions, or miss Earth even when its source appears well aimed. This entire system is called space weather. Because conditions around Earth can change rapidly and affect human technology. Spacecraft positioned upstream near the L1 point sample the solar wind before it reaches Earth, providing a final warning. Once the cloud reaches those monitors, forecasters may have only tens of minutes to confirm its most dangerous magnetic orientation. Utilities, satellite operators, airlines, and radio users can take protective actions when forecasts provide enough lead time. Power grids contain extremely long conductors, making them vulnerable to slowly changing magnetic fields. During geomagnetic storms, changing magnetic conditions create electric fields in the ground, which can drive unwanted currents through connected infrastructure. Engineers call these flows geomagnetically induced currents, or GICs, and they behave differently from ordinary alternating current. Unwanted current can push transformer cores toward magnetic saturation, increasing heating, distortion, and voltage control problems. Risk depends on storm intensity, local geology, grid design, transformer type, latitude, and the direction of transmission lines. Resistive rocks can force induced currents toward power networks, while more conductive ground may distribute them differently. High-latitude regions usually face greater exposure because auroral electrojets and magnetic disturbances are strongest nearer the poles. Long east-west transmission corridors may respond differently from shorter networks, so geography and engineering combine to shape vulnerability. Operators can adjust power flows, postpone maintenance, increase reserves, and monitor transformer heating before conditions worsen. In March 1989, a geomagnetic storm collapsed Quebec's power grid, leaving millions without electricity for about 12 hours. The Quebec system failed rapidly because protective devices reacted to voltage instability, spreading through the interconnected network. Individual components may survive, while the network still becomes unstable, because modern grids depend on coordinated voltage and frequency control. A disturbance can spread if operators lack margin, yet automated controls and careful procedures can also isolate trouble. Large high-voltage transformers are expensive, specialized, and difficult to replace quickly if severe damage actually occurs. Even extreme forecasts do not mean every transformer will burn. Outcomes depend on duration, orientation, geography, and preparation. False. Isn't and sexistentitions and the fry everything contrillition scripsens, and is celta kistens. Ordinary devices may stop working, mainly because electricity, communications, positioning, or timing services become unavailable around them. Spacecraft operate directly inside the disturbed environment, where radiation, charging, drag, and navigation errors can increase. Storm energy heats the upper atmosphere, making it expand upward and increasing drag on satellites in low Earth orbit. In February 2022, enhanced atmospheric drag after a geomagnetic disturbance contributed to the loss of 38 newly launched satellites. Even satellites that remain healthy may move differently than expected, forcing operators to update tracking and collision calculations. GPS works by measuring exquisitely timed radio signals, so small delays in the ionosphere can become significant position errors. The precision can collapse, fring mag decephanate, persistement try to sense a situs, becontris of the intrunsent, de 90 agent suts. The prickstudy summation contreat and 60 tented turrets, the true presenting to pestions and common nations countries entresemt. The Fasiver teen. Solar flares can disturb the ionosphere almost immediately, degrading high-frequency communication on the sun-facing side of Earth. Radiation effects can arrive in minutes, while the slower plasma cloud may produce geomagnetic disturbances much later. Telecommunications, finance, transportation, and power networks use satellite timing, making signal disruption a hidden systems problem. The internet does not live entirely in satellites, yet terrestrial networks still depend on power, timing, routing, and data centers. Fiber itself is not a giant antenna, but cable landing stations and powered repeaters remain part of a wider electrical system. Mobile towers may keep operating on backup power temporarily, but prolonged regional outages would eventually exhaust local reserves. Hospitals, emergency centers, water systems, and transport hubs plan for outages, though backup duration and fuel access vary. A brief disturbance is manageable. Widespread equipment damage and slow restoration would create the more serious societal consequences. The benchmark for extreme space weather remains the Carrington event, observed in September 1859 during the telegraph era. Induced currents sparked equipment, shocked operators, and allowed some telegraph systems to function after batteries were disconnected. Reports described auroras at unusually low latitudes. This revealed how dramatically the magnetic disturbance expanded across Earth. Telegraph networks were vulnerable, but society had no satellites, GPS, global data centers, or continent-scale synchronized infrastructure. A comparable event today would meet a far larger technological target, but precise damage estimates remain deeply uncertain. Researchers model different storm strengths, magnetic orientations, grid conditions, and recovery assumptions, producing widely varying scenarios. Another major geomagnetic storm in 1921 damaged telegraph and railway signaling systems, offering a second historical warning. The Quebec blackout proved that space weather could still disrupt a modern electrical system, long after the telegraph age ended. Powerful storms in 2003 disrupted satellites, aviation, radio, and grid operations, while auroras appeared at unusual latitudes. In July 2012, an extreme solar eruption crossed Earth's orbit, but our planet had passed that location roughly a week earlier. Had Earth occupied a slightly different position, scientists would have gained a direct modern test of a potentially Carrington-class event. The May 2024 G5 event, later named the Gannon storm, became the best instrumented severe geomagnetic storm yet observed. Measurements showed major changes from the upper atmosphere to near-Earth space, helping researchers improve models and preparedness. NASA observations found 2 temporary radiation belts created after the 2024 storm, including an unusual population of energetic protons. Despite reaching G5, the 2024 storm did not destroy civilization, demonstrating why storm category alone cannot predict every outcome. Storm severity depends heavily on how incoming fields connect with Earth, so similar eruptions can produce very different consequences. Even a historic solar storm would create uneven impacts, not a uniform global blackout occurring everywhere at once. Forecasts, grid procedures, satellite safe modes, route planning, and backup systems can reduce losses before the strongest disturbance arrives. Space weather centers issue watches, warnings, and alerts, so operators can respond as confidence and measured conditions increase.
Most people cannot shield a transformer, but they can prepare for ordinary outages with water, lighting, radios, and charged batteries.
Utilities can install monitoring, improve operational models, protect transformers, and study regional geology to manage geomagnetic currents. Spacecraft designers use shielding, fault-tolerant electronics, safe modes, and improved drag forecasts to survive disturbed conditions. Airlines can reroute polar flights, adjust altitude, and prepare alternate communications. When radiation and radio conditions deteriorate, banks and markets depend on precise timestamps, making redundant clocks and terrestrial backups important during navigation disruptions.
Critical facilities need generators, fuel, maintenance, and tested transfer procedures, because equipment alone does not guarantee resilience.
Electricity moves drinking water and wastewater, so prolonged outages can become public health problems. Even without damaged pipes, fuel delivery, refrigeration, traffic control, warehouses, and communications can amplify an electrical disruption across daily life. Minutes after a powerful flare, radio conditions may worsen, while operators begin evaluating the eruption and its trajectory. As the cloud travels, models refine arrival estimates, utilities review procedures, and satellite teams prepare for disturbed conditions. Upstream monitors finally measure the cloud's speed, density, and magnetic direction, revealing whether the worst-case coupling is likely. The first impacts tear the first impacts, design deployments at the mass system assisting timminenses contrations, as demonstrated present system. Control rooms track voltage, reactive power, transformer currents, and regional disturbances while adjusting the network defensively. Some areas could experience equipment alarms or outages, while others remain stable because exposure and grid conditions differ. If damage remains limited, systems may stabilize quickly. Destroyed transformers or widespread cascading failures would extend restoration dramatically. Costs would come from outages, satellite losses, rerouted transport, damaged equipment, delayed transactions, and disrupted production. Rumnant designing plies intranature intimation. Is a porous of excellings a penstrings can fear cells, and distinks of this storms. Phones, cars, and household electronics are not automatically destroyed merely because a geomagnetic storm reaches G5. Solar eruptions are continuously monitored, and Earth-directed clouds usually provide some lead time, though exact severity emerges late. A flare and a geomagnetic storm are related but distinct, so bright radiation alone does not guarantee a severe magnetic impact. The greatest risk comes from interconnected systems failing together, especially when power, communications, timing, and logistics overlap. Better measurements of CME magnetic structure, regional geology, grid response, and upper atmosphere dynamics would sharpen future forecasts. Another severe event is inevitable someday, but its timing, orientation, duration, and technological consequences cannot be predicted far in advance. Humanity cannot stop solar eruptions, yet forecasting, engineering, planning, and honest communication can prevent a hazard from becoming a catastrophe. Auroras reveal both the beauty of our magnetic connection to the sun and the vulnerability created by modern technology. Solar activity rises and falls over roughly 11 years, changing how often strong flares and eruptions become likely. Solar maximum increases activity, but an extreme Earth-directed storm can occur outside the exact peak and cannot be scheduled. A faster eruption can overtake a slower one, merging their structures and creating a stronger, more complicated arrival at Earth. Remote images reveal speed and direction better than magnetic orientation, which often remains uncertain until the cloud reaches upstream monitors. Geomagnetically induced currents can also enter long pipelines. This complicates corrosion monitoring and protection systems during strong disturbances. Long rails and signaling circuits can experience electrical interference, showing that vulnerability extends beyond familiar power grid headlines. Ground stations, satellites, utility monitors, and even widespread aurora photographs now provide complementary views of the same storm. The sun launches the disturbance. Earth's magnetic field transfers energy. Infrastructure converts that energy into risk, and preparation changes outcomes. A solar superstorm could cause serious regional and global disruption, but a permanent worldwide technological collapse is not the default outcome. The danger is real precisely because it is invisible. Magnetic changes in space can become currents, errors, outages, and costly decisions on Earth. Look closely at an ordinary pigeon, and you are looking at the surviving branch of the dinosaur family tree. Outside your window, dinosaur anatomy is still moving, balancing, breathing, nesting, and taking flight. Modern birds are not merely descended from dinosaurs. Scientifically, they belong inside Dinosauria. That conclusion emerged from thousands of fossils, anatomical comparisons, and discoveries that once seemed impossible. Feather impressions changed the debate because they preserved structures previously associated almost entirely with birds. Long before powered flight, feathers already covered many dinosaurs for functions unrelated to aviation. Insulation offers one likely early advantage, especially for small active animals losing heat rapidly. Visual display, species recognition, camouflage, and courtship may also have shaped feather evolution. Brooding provides another clue. Some non-avian dinosaurs sheltered eggs using postures strikingly similar to birds. The real story is not a sudden transformation. It is a long sequence of anatomical experiments spanning millions of years. Begin with theropods, mostly two-legged dinosaurs whose skeletons already contained several features later inherited by birds. 3 forward-pointing toes connected modern birds to a much older pattern of dinosaur locomotion. Shared proportions become clearer when the skeletons are placed side-side, rather than judged by appearance alone. Bipedal balance established a body plan that later changed as tails shortened and flight shifted the center of mass. Across avian evolution, long bony tails gradually yielded to shorter structures supporting movable tail feathers.
A compact tail improved aerodynamic control while reducing weight far behind the hips.
A bird wing is a modified dinosaur arm, not a completely new structure added later. A specialized wrist allowed feathered forelimbs to fold against the body, a motion retained by birds. The wishbone also predates true birds, appearing within theropod dinosaurs as part of the shoulder apparatus. Each inherited component became useful within a larger system, but no single bone created flight by itself. Early dinosaur feathers ranged from simple filaments to complex veined structures with very different functions. Complex flight feathers can be understood as modifications of simpler structures rather than an abrupt invention. Asymmetrical veins improved aerodynamic performance by controlling airflow more effectively along the feather. Forelimb feathers may first have assisted balance, braking, display, or controlled descent. One hypothesis proposes that flapping helped small dinosaurs gain traction while running up steep surfaces. Another pathway emphasizes controlled gliding from elevated positions before sustained powered flight evolved. Microraptor carried large flight feathers on all 4 limbs, revealing an aerodynamic experiment unlike modern birds. Its exact posture remains debated, yet the fossil proves that flight evolution explored more than one configuration. Evolution produced a branching landscape of experiments, not a simple march from ground dinosaur to modern bird. Long-term miniaturization within birdline theropods may have unlocked faster development, agility, and new ecological options. Smaller bodies altered balance, muscle demands, heat loss, reproduction, and the physics of moving through air.
Moving the center of mass toward the wings improved control during increasingly aerial locomotion.
Shoulder anatomy gradually allowed a larger stroke, an essential step toward effective flapping.
Expanded chest musculature later supplied the power needed for repeated wing beats.
Powered flight required coordinated motion, muscle force, feather control, and a skeleton capable of handling repeated loads. Bird-style breathing evolved from a theropod respiratory system built for efficient one-way airflow. Pneumatized bones' reduced mass supports preserved strength under mechanical stress. Weight reduction worked only because reinforcement and fusion stabilized the body where flight demanded it. Reproduction also linked birds with dinosaurs through hard-shelled eggs, nest building, and prolonged parental care. Exceptionally preserved deposits in China revealed entire feathered ecosystems once missing from the fossil record. Archaeopteryx became iconic because one fossil combined unmistakable feathers with many dinosaurian skeletal traits. Its wings carried advanced flight feathers, although flight performance probably differed from that of most living birds. Clawed fingers, teeth, and a long bony tail preserved the dinosaurian side of the anatomical mosaic. No sharp boundary separated dinosaur from bird. Transitional animals combine traits in unexpected packages. Classification depends on evolutionary relationships, not on whether a fossil looks halfway between two stereotypes. Archaeopteryx is important, but it was not necessarily the single direct ancestor of every later bird. Early bird evolution quickly produced numerous combinations of flight ability, feeding style, and skeletal design. Beaks and tooth reduction evolved repeatedly, changing weight, feeding mechanics, and dietary flexibility. Cretaceous birds occupied many feeding niches, rather than sharing one universal diet. By the late Cretaceous, avian dinosaurs had diversified across forests, coasts, lakes, and terrestrial environments. One major group, the enantiornithines, became widespread and successful throughout the Cretaceous. Different feet reveal how strongly early birds had already specialized for distinct ways of life. Specialization brings advantages during stable conditions, yet it can become dangerous when an entire habitat disappears. That vulnerability would matter enormously when the asteroid transformed global ecosystems. 66 million years ago, a large asteroid struck near the Yucatan Peninsula. The collision triggered immediate destruction, but the longer ecological crisis determined which lineages endured. Dust, soot, and aerosols reduced sunlight, cooling the planet and suppressing photosynthesis. Once primary production fell, food chains weakened from the bottom upward. Stored seeds could outlast living foliage, creating a temporary resource unavailable to many large herbivores. Seed eating may have helped some toothless, ground-associated avian lineages survive the darkest interval. Survival was selective. Most bird lineages also disappeared, while only a small avian branch crossed the boundary. The extinction boundary pruned the avian tree severely, rather than sparing birds as a whole. Small size reduced absolute food needs and may have supported faster population recovery. Shorter generations could help populations rebound once conditions began improving. Ground-oriented habits may have mattered because global forests were devastated after the impact. With tree cover gone, lineages dependent on perching and canopy resources faced extreme pressure. Recovery began with hardy plants and simplified ecosystems, rather than an immediate return to Cretaceous forests. Flexible diets offered options when familiar food webs collapsed and seasonal resources became unpredictable. Generalists can reroute their diets. Specialists fail when a single required resource disappears. Freshwater and shoreline habitats may have buffered some survivors from fire, forest loss, and abrupt food shortages. No single trait explains survival. A favorable combination probably mattered more than any one feature. Researchers infer survival strategies from fossils, living birds, plant recovery, and the ecology of the extinction boundary. The earliest post-impact bird fossil record remains incomplete, so every explanation carries uncertainty. Geology records the planetary crisis more continuously than bird skeletons record individual survivors. All retimethymus in sedition, distentlet commention dissensions, a gradual recovery. Avian survival may have passed through extremely small populations, vulnerable to chance and local conditions. Once ecosystems reopened, surviving birds expanded into niches left vacant by extinct competitors. Peaks diversified rapidly as birds exploited new foods, habitats, and behaviors. Feet changed alongside beaks, revealing ecological expansion across land, water, and recovering forests. From a narrow bottleneck emerged the extraordinary global radiation of modern birds. Modern birds still carry the evidence of their dinosaur ancestry in almost every part of the body. Scaled feet and three-toed anatomy make the connection visible even without feathers. Beaks, claws, scales, and feathers are specialized structures produced by inherited developmental systems. Embryology exposes deep similarities that adult appearance can hide. Brooding posture, nest arrangement, and parental care connect living birds with fossil dinosaurs. Behaviorally, the highly efficient avian respiratory system also has roots within theropod dinosaurs. Air-filled bones appeared before modern birds and supported an active respiratory design. Wishbones trace a structural continuity extending deep into the theropod lineage. Every wing beat activates a modified dinosaur forelimb assembled through gradual evolutionary change. Today's birds look radically different because one dinosaur branch diversified into more than 10,000 living species. Several popular shortcuts distort the story. Evolution was not linear, feathers were not invented for flight, and most birds did not survive. A branching tree better represents experimentation, extinction, and repeated anatomical innovation. Reconstructions combine evidence and inference, so plumage patterns and behavior often remain less certain than bones. Microscopic pigment structures sometimes preserve clues to color, but such evidence exists only for certain specimens. Living birds can illuminate possibilities, yet they are not perfect replicas of extinct dinosaurs. Good paleontology distinguishes fossil facts from likely interpretations and imaginative possibilities. The dinosaur-bird connection rests on converging evidence from many independent anatomical systems. No single feature carries the argument. Together, the pattern becomes overwhelming. Birds survived because one dinosaur branch reached the boundary with a useful combination of traits. The familiar bird on a sidewalk is not the opposite of a dinosaur. It is the result of dinosaur evolution. Across deep time, small anatomical changes accumulated into bodies capable of flight, survival, and feathers provided versatile structures. Miniaturization changed physics. Coordinated anatomy enabled flight. The asteroid did not create birds, but it determined which avian lineages inherited the post-dinosaur world. From limited survivors came an ecological expansion unmatched by any other living dinosaur group. Birds eventually occupied nearly every environment on the planet, including places no Mesozoic theropod ever experienced. Even flightless birds retain wings because evolution modifies inherited structures rather than starting from nothing. Ostriches demonstrate that living dinosaurs can abandon flight while preserving a deeply theropod body plan. Hummingbirds occupy the opposite extreme, pushing the inherited wing system toward remarkable maneuverability. One ancestral framework now supports behaviors ranging from deep diving to hovering flight. A feather can now stand for the entire story: inheritance, experimentation, catastrophe, and survival. The case does not depend on resemblance alone. It emerges from fossils, anatomy, development, behavior, and evolution. Birds survived the asteroid because they were already a diverse dinosaur lineage, not because evolution began afterward. Survival preserved only a fraction of avian diversity and erased every non-avian dinosaur branch. From that narrow escape came every living eagle, sparrow, penguin, owl, chicken, and pigeon. The age of dinosaurs never ended completely. One branch transformed the world above the ruins. Seen through evolution, a city bird becomes a deep-time survivor carrying millions of years of anatomical history. Fossils do not describe a dead world separated from ours. They reveal the ancestry of life still present. Dinosaur, survivor, and bird are not separate chapters. They are connected points along one evolutionary lineage. Once that connection becomes visible, ordinary birds never look ordinary again. The dinosaurs are still here, not as monsters from the past, but as birds living all around us. Look at this skyline. Nothing seems to move, yet the ground beneath it may be dropping year after year. Nothing appears broken at street level because subsidence often spreads slowly across neighborhoods instead of opening one dramatic hole. Yet satellites reveal motion too small for human eyes by comparing the ground from one pass to another. The ocean is only half the story, because flooding depends on water height relative to the ground beside it. Sometimes the shoreline becomes more vulnerable even when the ocean changes little, simply because the land itself moves downward. That difference is called relative sea level, the combined result of ocean movement and vertical land motion. Engineers call this downward ground movement land subsidence, a process that can be natural, human-driven, or both. Unlike a sudden collapse, regional subsidence may lower many square kilometers without producing a single obvious center. Whole neighborhoods can descend together, carrying streets, pipes, railways, foundations, and flood defenses with them. The danger grows when sinking land combines with storms, high tides, river flooding, or rising seas. Begin beneath the pavement, where the ground is not solid rock, but a layered mixture of sand, silt, clay, and water. Groundwater occupies tiny spaces between sediment grains and fractures, supporting part of the weight carried underground. An aquifer behaves like a water-bearing geological layer, not an underground lake with a giant empty ceiling. Pumping lowers hydraulic pressure around a well, drawing groundwatering water inward from the surrounding sediments. Water pressure normally helps hold sediment grains apart. Remove it, and more of the overlying load shifts onto the skeleton of the soil. Remove enough water pressure, and the weight above squeezes fine-grained layers that were previously supported from within. Clay and silt are especially important because their platy grains can compact when groundwater levels fall. Their grains rotate and pack closer together, shrinking the underground space that once stored water. Once compressed beyond its previous stress, part of an aquifer system may never regain the lost storage space. Surface elevation then drops because the total thickness of the underground sediment package has become smaller. Picture a thick stack of damp paper being pressed thinner, rather than a city falling into a hollow chamber. In this layers persistence intuitionmentations, layers react differently. Will continkle downs and vinuith commendanes fording disturs invitations. Large connected pores let water move through sandy layers more readily, making their pressure response relatively quick. Tiny pathways make water leave clay layers gradually, so compaction may lag behind the original groundwater decline. Delayed compression means land may keep settling even after officials reduce pumping or rainfall returns.
During drought, reduced rivers and reservoirs often push farms and cities toward heavier groundwater use.
Urban demand keeps growing through homes, factories, hospitals, cooling systems, construction, and public services. When withdrawals outrun natural recharge for long periods, pressure falls faster than the underground system can recover. The groundwater surface can descend beneath many wells, forcing pumps deeper and increasing the stress on compressible sediments. Each operating well creates a drawdown zone, shaped like a broad depression in groundwater pressure. Many nearby wells can overlap. This turns separate drawdown cones into a regional pressure basin. Overlapping pumping effects can lower an entire urban basin instead of damaging only the ground beside individual wells. Structures usually move with the ground beneath them, so a tower may remain upright while its absolute elevation quietly falls. Some districts descend faster because geology, pumping intensity, drainage history, and construction loads vary across the city. Uneven motion is often more damaging than uniform sinking because roads, pipes, and foundations must bend across the gradient. A few millimeters each year can accumulate across decades, especially where critical infrastructure was designed for a stable elevation. Surveyors compare permanent reference points over time to detect whether the land has moved vertically. Continuous GPS stations record precise position changes, revealing gradual uplift or subsidence at specific ground locations. Satellite radar can map movement across entire cities, covering far more ground than isolated survey points. Two radar observations taken at different times contain tiny phase differences caused by changes in the distance to the surface. Scientists convert that phase shift into a map of ground displacement along the satellite's viewing direction. Interferometric synthetic aperture radar, or INSAR, makes slow deformation visible as patterns across space and time. Colored patches represent movement toward or away from the sensor, not temperature, pollution, or political boundaries. Repeated radar scenes create time series that distinguish seasonal swelling from persistent long-term sinking.
Satellite measurements become stronger when researchers compare them with GPS, leveling, wells, and subsurface instruments.
An extensometer measures changes in aquifer thickness by anchoring deep below the compressible layers. Groundwater levels explain when pressure changed, helping scientists connect pumping cycles with later surface movement. Coastal tide gauges measure water relative to the land, so sinking ground can appear as faster local sea level rise. Local sea level change can differ from the global average because currents, gravitational effects, and vertical land motion alter the result. Useful flood maps must combine ocean projections, land motion, tides, storms, rivers, and drainage capacity. Once these measurements are combined, a city that looked stationary becomes a moving landscape with distinct deformation zones. Mexico City offers a powerful example because dense development sits above water-rich sediments deposited in an ancient lake basin. Long before modern streets, lakes covered much of this basin, and left thick layers of soft clay beneath later construction. Those lake clays contain abundant pore space, making them highly compressible. When groundwater pressure declines, millions of residents and businesses require dependable water, while local surface supplies cannot meet every demand. Heavy extraction lowers pressure within the basin, allowing the weight of the city and sediments to compact the clay. Because clay thickness and pumping vary from place to place, different neighborhoods descend at different rates. Historic structures can tilt or separate as foundations experience uneven movement across short distances. Water and wastewater networks crack when connected segments settle unevenly, creating leaks inside an already stressed system. Gravity sewers depend on carefully designed gradients, so subsidence can flatten, reverse, or fragment their intended flow. Depressed streets and altered drainage routes can hold stormwater where it previously moved away. Engineers can level a building or replace a pipe, but continuing ground motion may shift the same system again. Long-term subsidence accumulates quietly, turning small annual movements into major elevation loss across generations. The city pumps groundwater to serve residents, yet the resulting compaction damages pipes that deliver water and remove waste. Similar interactions between groundwater, soft sediments, infrastructure, and flooding have appeared in cities across several continents. Along the Texas Gulf Coast, historic groundwater withdrawal compacted soft aquifer sediments and lowered parts of the region. Where land sinks beside bays and estuaries, storm tides reach higher relative to roads, homes, and protective structures. California's San Joaquin Valley shows how agricultural pumping can compact aquifers far beyond a dense urban center. When surrounding land subsides, major canals can lose freeboard and carrying capacity even if their concrete walls remain intact. Venice illustrates how natural settling, past groundwater extraction, and ocean change can combine around a low lagoon city.
Tokyo demonstrates that strong pumping controls and alternative water supplies can greatly slow human-driven subsidence.
Bangkok's soft delta sediments and groundwater history reveal why low-lying cities must track both land and water. Shanghai represents another delta metropolis, where groundwater management, sediment compaction, and heavy development require continuous monitoring. Osaka experienced severe subsidence during intensive industrial groundwater use, showing how urban water policy can reshape elevation. Groundwater is often dominant, but oil extraction, gas production, mining, drainage, tectonics, and natural sediment settling may contribute.
Removing fluids from deep reservoirs can increase effective stress and compact the surrounding rock, in some producing regions.
Peat-rich ground can shrink and oxidize after drainage, causing surface loss through a different mechanism than aquifer compaction. Underground excavation may allow roofs or pillars to deform, transferring movement upward towards streets and buildings. Earthquakes and slow fault movement can raise or lower land independently of groundwater use. Far from former ice centers, the crust may still adjust as Earth's mantle responds to vanished glacial weight. Young river deltas and reclaimed coasts continue consolidating under their own weight, even without intensive pumping. Buildings, roads, fill, and infrastructure increase surface load, especially where soft sediments already compress easily. A very heavy structure can deform its immediate foundation zone, But citywide sinking usually involves broader geological and water processes. Blaming buildings alone misses the larger system of groundwater pressure, sediment type, fluid extraction, and regional geology. Even within one city, deformation may cluster around pumping centers, thick clay deposits, reclaimed land, or industrial zones. One block may remain stable, while another nearby sinks, creating sharp boundaries that strain shared infrastructure. Structural risk depends not only on total movement, but also on how rapidly elevation changes across distance. Foundations, pavements, and buried pipes tend to fail where bending and tension concentrate, not necessarily where sinking is greatest.
Rail lines, water mains, sewers, tunnels, and highways connect districts that may move at different speeds.
Small, repeated adjustments can shorten asset life, raise maintenance costs, and produce failures long before a dramatic collapse. Road surfaces deform when adjoining sections settle unevenly, creating dips that collect water and stress pavement. Railways require precise geometry, so gradual vertical distortion can force speed restrictions, repairs, or costly realignment. Many sewer systems rely on gravity, meaning a few lost centimeters can disrupt carefully engineered slopes. Pressurized water pipes may crack at joints where ground motion pulls connected segments in different directions. Compacting layers may buckle or shear well casings, damaging the very infrastructure used to reach groundwater. A flood barrier that sinks with the land loses effective height, even when its concrete body remains unchanged. Storm surge travels deeper into a subsided landscape because roads, wetlands, and defenses sit lower relative to the water. Regular tides can begin flooding streets at lower ocean thresholds once the surrounding ground has lost elevation. Lower land and altered groundwater gradients can help saltwater penetrate farther into coastal aquifers and soils. Permanent aquifer compaction reduces pore volume, leaving less underground space available for future water storage. Once pore structure collapses, rainfall or recharge may restore pressure without restoring the aquifer's original capacity. Lower-income districts often face older infrastructure, fewer repair resources, and greater exposure to recurrent flooding.
Flood models based on outdated elevation data may underestimate risk, where the ground continues moving.
Static elevation maps become stale. When subsidence changes faster than planning cycles and infrastructure upgrades. Waiting allows elevation loss, structural damage, and flood exposure to compound, making later solutions more expensive. Effective action begins with knowing where the ground moves, how fast it moves, and which mechanism drives it. Groundwater records and deformation data should be analyzed together because pumping decisions directly affect elevation risk. Limiting withdrawals before pressure crosses damaging thresholds can slow compaction and preserve aquifer storage. Where feasible, shifting demand toward rivers, reservoirs, or imported water can reduce dependence on compressible aquifers. Managed recharge directs clean water into permeable ground, so aquifer pressure can recover during wetter periods. Cities can store storm runoff for later infiltration instead of sending every rainfall pulse rapidly to the sea.
Reused wastewater can supply industry, landscaping, or recharge projects, reducing demand for fresh groundwater.
Water prices and pumping fees can discourage waste when they reflect depletion, infrastructure damage, and long-term storage loss. Paving over permeable land blocks natural infiltration, so planning must preserve areas where water can enter the ground. Permits, metering, and extraction limits give agencies tools to manage the biggest sources of pressure decline. Flexible joints, adjustable supports, and modular repairs can help infrastructure tolerate modest differential settlement. Levees, pumps, drainage networks, and evacuation maps must account for future land motion, not only future ocean levels. Regular satellite and ground measurements can reveal new hotspots before cracks, leaks, or floods make them obvious. Urban flood risk equals more than rising water. It also includes sinking land, altered drainage, and weakening infrastructure. The essential lesson is simple. Protecting cities requires watching the surface below our feet as carefully as the water beside them. Around 1200 BC, the Eastern Mediterranean was one of the most connected places on Earth. Kingdoms traded copper, tin, grain, timber, oil, textiles, and luxury goods across hundreds of miles. Bronze made the system possible, but bronze needed both copper and tin was often the harder ingredient to obtain. Palaces did not just rule. They stored food, organized labor, tracked goods, and held entire economies together. Information was part of the infrastructure too. Scribes recorded shipments, taxes, rations, and diplomatic messages. This was an international system where rulers wrote to one another, exchanged gifts, and depended on long-distance stability. It was a world of diplomacy and competition, where peace, trade, and prestige were tightly linked. And that made the entire system powerful, but also dangerously interdependent. Then, within only a few generations, many of these kingdoms and palace centers collapsed or changed beyond recognition. The mystery is not that one city fell. It is that so much of this connected world began failing at once. To understand the collapse, you first have to understand how much everyday life depended on fragile chains of movement and control. A single shipment could carry the metal that armed armies, repaired tools, and signaled wealth across an entire kingdom. Maritime trade was the bloodstream of the Late Bronze Age, especially in the Aegean and Eastern Mediterranean. The chain reaction risk. Food mattered just as much as metal. Palace systems had to collect, store, and redistribute grain to keep labor and authority intact. One major suspect in the collapse is climate stress, especially drought and the harvest failures that can follow it. Paleoclimate evidence suggests parts of the region experienced periods of aridity around the time the system came under pressure. Less rain can mean weaker harvests, tighter rations, higher prices, migration pressure, and political instability. And when food becomes uncertain, the letters from this period start sounding anxious, urgent, and sometimes desperate. One of the clearest windows into the collapse comes from Ugarit, a wealthy port city on the Syrian coast. Ugarit sat at a strategic crossroads, tied into trade networks that connected empires, islands, and coastal states. Its surviving tablets preserve something rare: the written voice of a system under sudden strain. Some letters mention enemy ships, missing support, and threats arriving too fast for help to organize. This is where the famous Sea Peoples enter the story, though they remain one of the most debated parts of the collapse. Ancient Egyptian records describe groups attacking by land and sea, but they do not solve who every attacker was or why they were moving. They may have included displaced groups, mercenaries, migrants, raiders, or peoples pushed by the same wider stresses hitting everyone else. The deeper problem may have been convergence, several shocks arriving in a system already stretched thin. When one major node in a highly connected network fails, the damage does not stay local. Fewer shipments mean thinner reserves, weaker armies, less authority, and rising pressure on every institution tied to the palace. A drought alone may not destroy an empire, but drought plus war plus supply failure can be devastating. At Ugarit, the crisis appears to have turned into sudden destruction. The surviving letters suggest officials were still trying to respond, even as the situation unraveled around them. Archaeology confirms fire, collapse, and abrupt abandonment at several places connected to the wider crisis. But the collapse was uneven. Not every city fell the same way, and not every region failed at the same moment. Farther north, one of the great powers of the age was also beginning to disappear: the Hittite Empire. The Hittites controlled much of Anatolia and competed directly with Egypt, yet their state also depended on logistics, grain, and loyal provinces. Texts from the era hint at food shortages.